Okay, back to 11.4 reverse chain rule. You've just done some questions from the exercise, but there's some harder ones that you need to be able to do as well. And these examples should cover those. So easy number 4 is integrating cosec squared x over 2 plus cot x all cubed with respect to x. And again, you have to spot it's one of those patterns again. But which one? Now it's a fraction, so let's try and think about f dashed of x over f of x, that pattern there, because the guess is always ln of the denominator. That's not going to work, is it? If you think about that, this power, normally the denominator ones hasn't got a power of 3, it's normally to the power of 1 effectively, or just by itself. So that one's not going to work. It's almost like a trick question. What you need to do first is this. Write it in index form. And now this one looks more like f dashed of x, f of x to the power of something. Because cot x differentiates to cosec squared. That's something you need to know. Anybody remember what the guess is for this? Well, add 1 to the power. So try y equals 2 plus cot x. Add 1 to this power, -2. Differentiate to see how bad the guess is. Times by the power. Subtract 1 from the power. But remember to times by that thing differentiated. What does cot x differentiate to? Negative cosec squared x. And this would simplify to 2 negatives make a plus. So 2 cosec squared x brackets 2 cot x to the power of -3. How bad is the guess? It's out by a factor of 2. So my initial integral, which I'll call I, is equal to half of my guess. Half 2 plus cot x to the -2 plus c. That would be it. So yeah, fractions normally 95% of the time would be the ln one, this pattern. But if you've got a bracket to a power and the power is not 1, then it's actually negative reciprocal stuff, negative power, and then the other rule. Okay, let's try one more example. E.g. number 5. Okay, now this one's the toughest by far. I'd be very surprised if any of you could do this without any help. It's got limits, not a big issue. We've done these in a previous subsection. But this bit is tough. Okay, so let's try and do it. So integrate 0 theta 5 tan x sec to the 4x dx equal to 15 over 4. Okay, which one is it? Now, it is going to be the f dashed of x, f of x to the n1. However, not quite what you expect, because, right, if I write that sec to the power of 4 like this, let's see if the pattern works for this. Sec x to the power of 4, sec x to the power of 4. I'd expect f dashed of x to be on the outside, but sec x doesn't differentiate to tan x. It actually differentiates to sec x tan x. And all the sec x's are in that bracket, so it doesn't look like it works. But you need to know a trick, this trick. integrate 0 to theta. I'm going to bring one of the sec x's out of that power of 4 and write it as this. Sec x cubed instead. Now check this rule. Sec x to the power of 3 to the power of 3. What does sec x differentiate to? Sec x tan x. It might work. So based on that now, I'm going to guess the bracket, add 1 to the power of 4, differentiate 4 sec x to the power of 3, bring the power down, knock 1 off the power, times by that bracket differentiated. Which is 4 sec x tan x. Not the tidiest. I could probably simplify that, but if I want to just make the comparison to what I want to get, I guess it's giving me a 4 sec x tan x, sec x cubed. I want a sec x cubed, I want a tan x, I want a sec x, but I want a 5 instead of a 4. So how can I create that? Well, call that I. My guess is out by, let's get this right, 5 over 4. Because you want to divide by 4 and then times by 5 to get the 5. So sec x to the power of 4. And remember, this had limits. So no plus c needed. If you wrote it in, it'd be pointless. Between 0 and theta. And that needs to be 15 over 4. Okay. Slightly run out of space. Substitute everything in. 5 over 4. Sec to the 4 theta, subtract 5 over 4 sec to the 4 of 0 is equal to 15 over 4. Don't touch that one yet. 5 over 4 sec to the 4 theta. Okay, let's work this out in the calculator. 5 over 4, you should be able to do this in your head though. 1 over, sec is cos, so cos 0 to the power of 4, give you 5 over 4, is equal to 15 over 4. Okay, I'm going to skip a couple of steps. Sec theta, so you would add 5 over 4, divide by 5 over 4, and then take the 4th root. If you take the 4th root, you do get a plus or minus. So 15 over 4, add 5 over 4 is that, divide by 5 over 4 is that, then take the 4th root, root 2 actually, to be exact, root 2, to give you two possible answers. Now this would give you cos theta is plus or minus the reciprocal, flip everything, 1 over root 2, to give you theta equals, let's do inverse cos of 1 over root 2, the plus 1, pi by 4, or inverse cos of minus 1 over root 2, 3 pi by 4. Now, you can't have two answers for this, but there's something in the question we haven't used yet. So we look back at the question. What haven't we used? This, theta between 0 and pi by 2. So we discount that answer, and that would be your final answer. Let's check to see if that was right. Integrate 5 tan x 1 over cos x to the power of 4 between 0 and my answer, which is pi by 4. Make sure you calculate this in radian mode. Moment of truth. $15.04, yes, that's correct. So I know I've done it right. And that's pretty much it. Now, I need to do a few more questions in that same exercise as you started earlier. So we are looking at page 303, and we're going to try effectively questions 4, 5, and 6. 4, 5, and 6. If you can't do any of those, let me know in the chat and I'll send you some hints and solutions or whatever.